Hello everyone, the power of pi here, and today we're going to be looking at the 2007 AIME II problem 13. So here it is. A triangle array of squares has one square in the first row, two in the second row, and in general k in the kth row for 1 less than or equal to k less than or equal to 11. So with the exception of the bottom row, each square rests on two squares in this row immediately below. In each square of the 11th row, a 0 or 1 is placed. Numbers are then placed into the other squares, with the entry of each square being the sum of the entries in the two squares below it. So for example, this one over here would be the sum of these two guys, and so on and so forth. So for how many initial distributions of zeros and ones is the bottom row? In the bottom row is the number on the top square a multiple of 3. Okay, so how I'm gonna approach this is I'm gonna let the bottom row consist of the numbers x1, x2, x11, where each xi is either a 0 or a 1. So now let me just simulate what will happen as we go up. As we go up to the next row, we basically add x1 and x2. That's precisely what this is. x1 plus x2, and then x2 plus x3, and then all the way until we have x10 and x11, and we add them to get x10 plus x11. So next, what do we do? So we'll add these two elements. So we have x1 plus 2x2 plus x3, and so on and so forth until we have x9 and x10, and then x10 and x11, and adding will give us x9 plus 2x10 plus x11. Okay, so what I'll do is I'll call this the 0th row. You'll soon see why. I'll call this the first row, and I'll call this the second row. So if you don't already see a pattern, let's just go through another one. If we consider the third row, it'll consist of the elements. We have x1 plus 2x2 plus x3. Next will be x2 plus 2x3 plus x4. So adding, we get x1 plus 3x2 plus 3x3 plus x4, and then so on and so forth until we have x8 plus 2x9 plus x10 and x9 plus 2x10 plus x11, which gives us x8 plus 3x9 plus 3x10 plus x11. So as of now, you should probably see the pattern. It's precisely the binomial coefficients. In other words, the kth row will have 11 minus k elements, and each is enumerated by the binomial coefficient, like k choose 0, k choose 1, k choose 2, k choose 3. K choose 0, k choose 1, all the way until k choose k. So if we simulate the process, the 10th row, which is this row, will have one element, and that one element is precisely equal to x1, or 10 choose 0 x1, plus 10 choose 1 x2, plus all the way until 10 choose 9 x10, plus 10 choose 10 x11. Okay, so now we know that this is the element on the very top row. Now we're given that for how many initial, basically xi's, do we have the top square a multiple of 3? So our goal should be to reduce this modulo 3. So 10 choose 0 is 1. 10 choose 1 is 10, mod 3, that's 2. So congruent 2. 2x2. And then 10 choose 2 is 10 times 9 divided by 2, which is 45. That goes away. 10 choose 3 is 10 times 9 times 8. By 3 times 2. We see a 3 here, so that goes away. 10 choose 4. Let's see 10 choose 4. Again, if 10 choose 4 should go away as well. I'm sure you can make the argument, 10 choose 5, 10 7. I'm sure you can make an argument that, like, for some k, we'll always have a 3 and some we won't. We see a 3 here, and it doesn't seem to go away. So 10 choose 4, reducing in mod 3, that becomes 0. How about 10 choose 5? I happen to have that memorized. It's 252, but if we were to go with the same process, this cancels. We see a 9 has a 3. So 10 choose 4 is a multiple of 3. Therefore, 10 choose 6 will be a multiple of 3. And so on and so forth. 10 choose 3, 10 choose 7, 10 choose 2, 10 choose 8. So the only things we have remaining is, this is congruent to. So x1 plus 2x2, and then x10. X10, or this is actually just x2. 10 is congruent to 1 mod 3. And then 10 choose 8 will go away, so we're just left with x10 and then x11. So this is what it is modulo 3. So now, since if we recall, every xi is either 0 or 1, therefore the sum is maximum of 4. So either we have two cases, case 1, which is x1 plus x2 plus x10 plus x11 is 0. This happens in one way, or case 2, where x1 plus x2 plus x10 plus x11 is 3. In this case, we choose 3 of them to be 1s and the other to be 0, and 4 choose 3 ways. And then after this is determined, so 5 possibilities in this case, any of the remaining xi's can take on a value of 0 or 1. We know that when we simulate the process, the only things that really matter are x1, x2, x10, x11. So we have a binary choice, and then we have 7 elements remaining. Yes, 7 elements. 4 here, so 7 remaining. So this is how many possible sequences of the 11th row there are. This is 5 times 2 to 7, which is 5 times 128, which is 640. And we are done. So hope you enjoyed this nice kind of Pascal triangle problem. Make sure to subscribe so you don't miss out on a future video.